Okay, everybody. So here is what. Oh, hold on. Okay, no, it's recording. I got worried I forgot the audio again. So here's what I've got on the list for problems for us to work on. If you got a question, just type it into the chat and we'll get to it at the end of the queue. We've got mastery question set 3, problem 1, prep activity 1 for emissions lab, part 1 and part 2 to that. We got practice set 3, problem 8. And then if we've got time, mastery question 2, problem 2, which is in yesterday's video, but I'm always happy to redo questions. I'm going to start with doing mastery question set 3, problem 1, and that will lead us into the prep activity. Because both of those deal with the photoelectric effect. So quick yes, no, using click on participants to put yes or no. You feel like you understand the photoelectric effect. And that is mostly no's and a couple of yeses. Okay. So essentially the photoelectric effect, and it's not something that's really very chemistry driven. It's something that we can relate to some ideas in chemistry, but the idea is essentially you've got a chunk of metal, you shine light on it, and out comes an electron. Now this is going to be important to chemistry for two main reasons. Main reason number one is it relates to this idea of ionization energy. It's not exactly the same, but atoms holding onto electrons and getting those electrons off is kind of a big part of chemistry when we start looking at reactivity. The other reason that this is going to be important, this is the photoelectric effect. The other reason this is going to be important is because it's one of the main experiments that gave this confirmation of quantum mechanics and revolutionized the way that people were thinking about electrons around nuclei. Albert Einstein is the person who did this, and we get this equation where the kinetic energy of the electron is going to be equal to the energy of the photon minus the work function, where the work function is essentially how much energy it takes to remove an electron. So you can imagine this piece of metal, whatever this piece of metal is, it holds onto the electrons with some amount of energy. And we have to hit those electrons with at least enough energy to knock them loose. And then any extra energy, so if we had exactly the right energy in the photon, we'd have no kinetic energy. If we have extra energy in the photon, however much extra energy we have above the work function, that's going to be in the kinetic energy of the electron. And this was a big deal because before this was done, the only person who really thought that the energy of the photon was related to wavelength was Maxwell Planck. Albert Einstein came by, said, look, I just redid the same thing that Maxwell Planck did for a completely different experiment. It's actually going to be the energy of the photon is going to be related to hc over lambda. So let's go ahead and think about how this rough understanding relates first to mastery question set 3, problem 1. And then we'll look at the emissions lab prep activity, which is also asking about photoelectric effect. So let's go ahead and get this ready. So that's our, before I erase all of this, questions about that kind of quick understanding? You can use the raise hand function, or you can just click, or you can just unmute yourself and ask. Okay, so let's go ahead and look at what mastery question, and this is I read it and I scratched my head for a minute and I was like, So mastery question 3 actually requires us to have a pretty good understanding of those ideas that we were just going over. So if you haven't watched Dr. Scott's video on the photoelectric effect, that might make it so this problem has a little bit more sense to it. But let's take a look at what's going on here. It takes, and these are my numbers, your numbers might be a little bit different than mine. It takes 279.7 kilojoules of energy to remove 1 mole of electrons from 1 mole of lithium atoms on the surface of lithium metal. What is the maximum wavelength of light that can remove a single electron from a single atom on the surface of lithium metal? Just the wording of it kind of makes me take pause and scratch my head a little bit. So let's go ahead and see if we can figure out the kind of essential things. As I approach any problem, I first start out by writing the explicit energy, the explicit information. 279.7 kilojoules per 1 mole. That's the only number I'm given. So that's the only number I'm given. The ultimate question is maximum wavelength. To remove 1 electron, right? That's what we're trying to get. So now we know what we're trying to get. And there's also a really important clue into what we should be thinking about. Right away, it's hard to tell with just this little bit of explicit information and this question, it's hard to tell what concept it's trying to get us to think about. But there's a couple important terms. Maximum wavelength and when we see the idea of maximum wavelength together with metal surface, those two ideas together should make us think photoelectric effect. You notice no place in the problem does it say, oh, use the photoelectric effect to do this. No place does it mention kinetic energy of electrons or any of those things that usually make us think about photoelectric effect. So in order to even start this problem, we have to have a pretty good conceptual understanding of photoelectric effect so we can connect these ideas together. And just so everyone knows, a couple people just came in. This is mastery question 3. Set 3, problem 1. So those two things together should make us think photoelectric effect. And then there's another thing that we should think about when we see that idea maximum wavelength. Another important idea one thing I always encourage, take the time, if you're not reading the entire textbook, which is not something I always encourage, at least read the key terms at the end of the chapter and the section summaries, at least. Because threshold wavelength connects to this idea of maximum wavelength, and if we don't know what this means in the photoelectric effect, again, we're stuck on the problem. So we have to have a good conceptual understanding to get to the mathematics. The math isn't going to be that hard, but the concepts that lead us to the math is kind of the essential part. So when we've got threshold wavelength, this is kinetic energy of the electron approximately equal to 0. So thinking back to that picture that I drew, we've got our metal surface, we've got light shining on it, we hit it with low energy, long wavelength, no electrons are coming off. We have to hit it with a certain amount of energy to get an electron to shoot off. And we can imagine that spot where it goes from no electrons to some electrons, that's going to be the threshold. And that's going to be right where the kinetic energy switches from 0 to just barely not 0. And so we're going to be looking for that idea where the kinetic energy of the electron is 0. So conceptual work is, this is kind of the implied information. Right? That's the hidden information inside of the problem. Right? This is the explicit, this is what it's asking for. The implied information, that hidden information that the problem assumes we've got conceptual understanding to get, is the kinetic energy is approximately 0, and kinetic energy equal to energy of photon minus work function. So let's go ahead and actually solve the problem now, and we'll see that math isn't going to be that difficult. It's addition, subtraction, multiplication, division. However, the work it takes to get to that math is the challenging part. So we're going to plug in a couple things. Instead of just saying kinetic energy is equal to the energy of the photon, we can say kinetic energy is equal to hc times 1 over lambda. I am writing this a little bit funny because I'm also getting us ready for thinking about the prep activity. hc times 1 over lambda minus work function. Foreshadowing. Just a little foreshadowing for the prep activity. Y equals mx plus b. Don't need that for this problem, but a little foreshadowing. Let's go ahead and plug in the values that we know. We know, since we're looking for this maximum wavelength, smallest energy, kinetic energy is approximately 0. We know Planck's constant, 6.626 times 10 to the minus 34. We know the speed of light, 2.99 times 10 to the 8th. We do not know the wavelength. That is the thing we are trying to solve for. And it appears we don't know the work function, but that's where this piece of information comes in. Right? This energy associated with removing an electron, that's going to be the work function. How hard is it to remove an electron? So we can actually get this, and we have to be careful about units. Right? This is kilojoules per mole, and right now this term, oh, speaking of units, I should have had units on here. This is joules seconds. This is meters inverse seconds. This is going to be 1 over meters. Notice this term is going to be in joules for a single electron. We've got kilojoules per mole. So let's go ahead and do a quick conversion. 2.79, oh wait, lies. 279.7 kilojoules per mole. We're going to have to multiply by 1,000 joules. Sorry, it's scrunched on the side of the board. 1,000 joules per kilojoule. And then we're going to have to multiply by 6.0, nope, divide by 1 mole. I want moles to cancel out, so I'll have my 1 mole on top, and I'll have 6.022 times 10 to the 23rd on bottom. And we should get a value. Now, also with our thinking ahead, conceptual understanding, when we're looking at wavelengths of light, we're usually on the order of 10 to the minus 19 joules if we're looking at visible light. If we're looking at infrared, we're going to see something that's smaller, like 10 to the minus 21. If we're looking at ultraviolet, we're going to be looking at an energy that's bigger, something that's like 10 to the minus 18. But this means when I get a value here, I should get something on the order of 10 to the minus 17 up to the 10 to the minus 22. I should be in that range. If I get a different number than that, we've made a mistake. So let's see, 2.797. I just did the point in the wrong. 279.7 times 1,000 divided by 6.022 times 10 to the 23rd. And sure enough, if we do that calculation, we get 4.59 times 10 to the minus 20 joules. Right? Notice Units are going to work out here. I'm going to have seconds cancel out. I'm going to have inverse meters cancel out. I'm going to have something in joules and something in joules. So units are going to work out. And at this point now we're just doing math. The algebra is not that hard. We're going to solve for lambda. Lambda is going to be our answer. We just have to be careful. It wants the answer in nanometers. So we have to make sure this is going to be an answer in meters when we solve. We have to make sure we convert to nanometers. What was that?
I got a different answer for when we converted it. I got 4.645 times 10 to the negative 19.
You might have a different value given than mine.
I have the same value.
You have 2797? 279.7?
Yeah.
Well, let me see. Did anyone else punch it in the calculator and see if I made a mistake? 279.7 times 1. Oh. Wait, what number did you get?
4.645 times 10 to the negative 19.
You're right. I put 279.1 instead of 0.7. Just threw it off by a little bit. 465?
4.645.
Okay, 64. 10 to the minus 20?
Negative 19.
You got negative 19. Let me check that part. So if you had me in class ever, you would notice when I'm in front of a classroom, I never use a calculator because it creates all kinds of confusion like this. Yep, negative 19. So I had a couple little calculator mistakes. I was still in the right ballpark. I probably just missed a 0 when I was punching into my calculator. This is part of why it's really nice to study with people, because they help you out. We're doing mastery question set 3, problem 1. Now that we fixed those two typos, we can just do the algebra for getting our final answer for this. So I'm going to subtract over. I'm going to have 4.645 times 10 to the minus 19 is equal to, I'm going to multiply those two numbers together as well. It's equal to 1.981 times 10 to the minus 25 times 1 over lambda. So we'll go ahead, we'll bring the lambda over and the 10 to the minus 19 down. And we'll get lambda equals 5 by 4.645 10 to the minus 19. We get lambda is equal to 4.265 times 10 to the minus 7 meters. We can convert that to nanometers. We've got 1 times 10 to the 9. We've got a whole lot of nanometers in 1 meter because nanometers are tiny. That's going to give us 426.5 in nanometers. Pretty involved problem in terms of needing conceptual understanding in order to do it. So that was mastery question set 3, problem 1 for those that just came in. And it took a lot, even though the math was not that hard, it took a lot of conceptual understanding to get to that math. Dr. Scott's video, Dr. Neff's video, Dr. Scott's video on photoelectric effect, Dr. Neff's video on photon energy, a couple things like that. Prep activity 1, so the questions we have on Q are prep activity 1's problem 1 and 2, practice problems 3, set 3, problem 8, and then a couple others. If you've got other questions that aren't on that list, go ahead and throw them in chat and we'll get to them. So this photoelectric effect and this kind of understanding of photoelectric effect is actually really necessary for doing the prep activity. So let's go ahead and take a look at that. Any questions about this before I erase it all?
Yeah, I have a quick question. Why do we use Avogadro's number to convert from moles?
So Avogadro's number tells us how many things, right? And this was a function of the problem. The problem gave us the energy in terms of kilojoules per mole, right? It said it takes 279.7 kilojoules of energy to remove 1 mole of electrons, but it wanted to know how much energy it took to remove 1 electron. And so Avogadro's number I always write it as things, right? So it's 6.022 times 10 to the 23rd things. In this case, the things are electrons from atoms. So we had to use that to get it so the answer was in terms of the wavelength for 1 electron, not for an entire mole of electrons.
Okay, thank you.
Okay. Other questions before we go on? Okay, so we're going to go on to prep activity 1. I see the question about prep activity 2 as well. But let's go on to prep activity 1. So prep activity 1, a couple things I'll mention about this real quick. Thing number 1 I'll mention is if you watch last week's video from Dr. Scott on the Excel intro, it actually does a step-by-step walkthrough of how to do this problem. So Dr. Scott, and if you watched that video, you might not have realized that he was doing this prep activity, but prep activity 1 is done by Dr. Scott in that video. The other thing is, it's really just trying to get us, it's more practice with Excel, and particularly with this idea of how do we relate a idea, like a thing in the physical world, like the photoelectric effect, like Planck's equation, like Beer's law. How do we relate that thing that we want to physically represent to our mathematics, particularly in terms of making a plot? So last week we did the A equals epsilon BC, and we related that to a line. This week we're going to do a couple different things related to lines. And one of them is going to be looking at the photoelectric effect. Kinetic energy equals Hc. Again, I'm going to write this in a really suggestive way. And we can line up, so this is the equation for the photoelectric effect. This has some physical meaning. This is something we observe in the physical world. And we're going to make plots, and if we make our plots in terms of kinetic energy versus 1 over wavelength, my y values will line up with kinetic energy. My 1 over wavelength will line up with that. Then my intercept will be the work function, and my slope will be Planck's constant times the speed of light. So let's go ahead and take a look at this. So if we make our plot correctly, we should be able to read the answer for part 1 and part 2 just right off of our graph. So I'm going to go ahead and switch to my computer screen. Okay, so looking at this in terms of what we have in Excel, the prep activity is really asking us to do these different plots. So this data is right now meaningless unless we put in labels. We've got our wavelength, and that's going to be in nanometers. And this is going to be the kinetic energy times 10 to the minus 19. So there's an important note inside of the prep activity that says if your kinetic energies are in the order of 10 to the minus 19, you have to multiply, you have to divide by 10 to the, oh wait, let me check. Oh, sorry, these are not in 10 to the minus 19, these are in 10 to the positive 19. And we're going to have to divide by 10 to the 19 to get it into joules. So I'm going to set up a quick little equation. My number divided by 1e19.
I have a quick question. Do we all have the same data?
I don't know if we all have the same data. Does your data look the same as mine?
My wavelengths do, but my kinetic energies don't.
I think we all have the same wavelengths, but different kinetic energies.
smaller number, I mean a bigger number than you would say.
How much bigger? So we should be expecting numbers on the order of 10 to the minus 19 joules. Visible light range kind of ideas.
Because mine ends with 3.63. Is that okay?
Times 10 to the minus 19?
Yeah.
Oh yeah, that's fine.
Okay.
So I can go ahead, rather than repeating that calculation, if I just double click there, boom, there are my kinetic energies in joules. Now, if I want this to work out, as you saw on the board just a moment ago, we really need our units to match up. So I don't want my wavelength in nanometers. I want my wavelength in meters. So I'm going to go wavelength in meters. That's going to be equal to my original wavelength times 1e minus 9. Oops, that's not 9. And I'm going to go ahead and format my cell because I like scientific notation. Format cell. Oh, I just realized, well, I think you all can't see that too well.
I have a question.
Yeah.
Is this being recorded?
It is. I hope. We'll see. So now I've got my wavelengths in meters and my energy in joules. But I don't actually want my wavelength in meters. Again, if we look at the board, we want wavelength in inverse meters. So I'm going to do one more thing. I'm going to make another column that's going to be 1 divided by wavelength in meters. And if we want to be fancy, we can come over here. We can make that the Greek letter lambda. I'm feeling fancy today. Greek letter lambda. So I'm going to set this equal to 1 divided by that thing. Okay. Now I should be able to make a plot of kinetic energy versus wavelength, or inverse wavelength. Kinetic energy on the y-axis, inverse wavelength on the x-axis. And there's a couple different ways we can do this in Excel, and I kind of do it the lazy way. What's up?
Can I ask a quick question going back?
Sure, of course.
When you plugged in to transfer your kinetic energy to joules, what exactly did you put in the formula spot?
So I put the kinetic energy divided by 1 times 10 to the 19.
Thank you.
You bet. And if you read the directions just above the problem, it says, reminder, the reported energies are multiplied by 10 to the 19, so all of your energies need to be divided by that value to get the value in joules. And it just has to do, the reason we did that was just the way that LabPal generates random numbers and displays numbers. It was much easier to do it all in terms of kind of whole numbers and then have that extra factor of 10 to the 19. We weren't trying to be extra tricky. So in order to make my XY plot, I like to have my values next to each other. So I'm going to go ahead and copy all my kinetic energy values and just paste them over here. And I'm going to specifically paste just the values. I'm going to do the same thing with my inverse wavelength. I'm going to copy that, and I'm going to paste just the values. So these aren't equations anymore. I lost my formatting. But that should make it so when I highlight these and I insert my XY scatter, ta-da, there's my graph. My graph is wrong. Let's talk about some of the ways we can tell my graph is wrong. So before I even put on the slope and trend line fit and all of that, if you just look, and I always have to double check when I'm making my graphs, I want my kinetic energy on the y-axis. It's on my x-axis. I want my inverse wavelength on the x-axis. It's on my y-axis. I've got my axes flipped. There's 2 ways to fix this. What I consider the right way to fix this is to go through the Select Data menu, click on Series, click Edit, and then you can select your x and y values. You can actually select x values here, you can select y values here. Hopefully I got them all. Hit OK. Hit OK. Now my x and y flip. I think that's the scientifically correct way to do it. The kind of the other way to do it, and the reason I like it that way is because it works whether you're on Macs or PCs. The other fixes depend on which version you're on. So I just flipped the order of my columns, and that also flips it for me. Most people think that way is easier because then you don't have to go in and like accidentally do something. But it requires you to kind of have these extra columns of information. I didn't have to make these columns. If I just went in and selected the data, I could have done it from this table without having these extra columns. So now, so after you copy, you can click on paste and don't hit Control V, but hit the actual where it says paste, and you'll notice there's this little drop down. And if you click on the drop down, there's an option that says paste values only. I don't think you can see that through Zoom, but you'll be able to see it on the recording. Zoom has trouble with embedded menus. So you can paste just the values that way. We can then go ahead and go chart design, add trend line, and we're going to do a linear trend line. I'm going to click on just the trend line, hopefully, yep. And I'm going to format the trend line. That's going to open up the secondary menu. I'm going to display equation, display r squared. And I want to do one more thing with that. I want to open up the label options. And I want to make sure I switch it to scientific with some decimal places. So now I've got this. And then another thing I always like to do is I like to crank that font up. Since the line fit's the most important thing, I like to make it real big and easy to see.
For the formatting the trend line, did you not set intercept for a reason?
Yes, right. The intercept in this case, we don't necessarily know what the intercept should be. When we're plotting actual data, the intercept could be an indication of some experimental error. If we're expecting it to be 0, that could be some experimental error. In this case, we don't expect it to be 0. We expect it to have some energetic value associated with it. So we want to calculate that intercept. That's actually going to be the answer to part 2. I see 2 hands up. Questions? You can go ahead and unmute yourself and ask. Let's see if I can see the list.
I just have a separate question. It's not related to this, so I was just going to wait until you were done.
Cool. If you throw it in chat, I'll get to it as soon as I'm done with this.
Okay.
So at this point, we've got our slope. That should be the answer to part 1. It's just that number, 1.98 times 10 to the minus 25. That value should be Planck's constant times the speed of light. And actually, if you take your calculator and plug in Planck's constant times the speed of light, you get 1.98 times 10 to the minus 25. So this data fits really well. For part 2, use your line equation from part A to figure out what the value of work function is for your particular mysterious metal. So it's got different data sets depending on which mysterious metal you have. For us, with our mathematical understanding of how this math line fits to our physical equation of photoelectric effect, it would just be 3.34 times 10 to the minus 19 would be the work function. Remember, because it's minus b, and since that's negative, that's going to be the work function.
So should we all have gotten the same slope?
No. Oh, you should have gotten the same slope, yes. Not the same intercept. Or close to the same slope. Assuming that you're in you have consistent units. You're dealing with inverse meters and joules. You should have, all of us should have, since the speed of light and Planck's constant are constants, all of us should get approximately the same slope.
So that means the y-intercept is the work function, basically?
Yeah, the y-intercept's the work function.
And so now I notice I have two variables. I have kinetic energy and wavelength. Are one of those, do we know one of those? Is wavelength the slope?
So which problem are you looking at?
For number 2, isn't my equation going to be kinetic energy equals potential energy minus work function?
Yeah, but we can just, if you can see my screen here, I'll stop sharing this. So we can see we actually don't have to do any additional calculation. Once we have that slope, and intercept, that intercept, just reading off the equation for the line, is the work function. So we don't have to do any additional calculations after we do the fit.
Yeah, sorry.
No worries. This is a really important concept in chemistry that we don't always get in mathematics. Right? Mathematics goes through a lot of the kind of conceptual ideas of how you do math, how you make plots, how you can do different line fits, all the different mathematical functions you can get. Chemistry and physics kind of take that mathematics and say, hey, we can represent physically real things with the mathematics. And that's really what makes mathematics such a great thing to study and such a powerful tool in science, is we can make these relationships between the math and the physical world.
So you're saying that if we just look at our entire equation, that's our work function?
Yeah.
The whole thing in? Okay.
Well, just the intercept at the end is the work function. Just the intercept. Master question 2. Okay. Let's see. So that was prep 1, emissions prep 1, part 1 and part 2. The other questions I have practice set 3, problem 8, and I see mastery questions set 2, problem 3, and problem 2. Both of those were done in the video yesterday. I'm happy to go over them again, but if you don't want to wait, you can go watch the office hours from yesterday. Let's take a look real quick at practice set 3. Unless are there any other questions about the first prep activity?
Yeah, could you maybe go over the last question on the first prep?
Yeah. Let's see. So looking at the last question, this is question 3.
About the wavelength?
Yeah. So the photoelectric effect only occurs when a photon's energy meets or exceeds the threshold value of the metal it is impinging on. For your mystery metal, what is the maximum wavelength in nanometers of the photoelectric effect? So let's go ahead. I'm going to try redrawing my plot real quick, just to give us a rough idea. I had a set of data that kind of looked like this. We had our 1 over wavelength here. We had our kinetic energy here. This was in joules. This was in meters. Sorry, this was in inverse meters. 1 over wavelength. And we had our line fit. And you'll notice there's a spot where we cross from positive kinetic energy to negative kinetic energy. Does that really make sense? No.
Yeah.
It doesn't, right? So essentially what happens is all of these wavelengths are places where no electrons are being ejected. We don't see anything happening. And it's only right here at the x-intercept where we get something to start happening. That's the threshold wavelength. So we can go ahead and we can solve for the x-intercept pretty easily, mathematically speaking, if I rewrote the problem and just said, what's your x-intercept? You just set y equal to 0, solve for x. It's super easy. Right? And that's all the problem is asking for, but it wants us to have the conceptual connection to the mathematics. Right? It wants us to understand that finding that x-intercept isn't just a mathematical exercise we're doing, but it has this relationship to the physical phenomena that we're looking at. So looking at my equation that I had, for my line fit, I had y equals 1.98 times 10 to the minus 25x minus 3.34 times 10 to the minus 19. I want to find the x-intercept. That means when y is equal to 0. So I'm just going to do some quick rearranging. I'm going to get 3.34 times 10 to the minus 19 is equal to 1.98 times 10 to the minus 25x. Solve for x.
Okay.
Now, you're not going to be done. Don't forget. There's an important don't forget here.
And then you have to take the reciprocal.
Yeah, the x is going to be inverse wavelength. So we have to remember to flip that to wavelength. So we're going to have to take the reciprocal.
Cool. I think what kind of stumped me is that they're asking for like the maximum wavelength.
Yes.
But wouldn't that be the minimum that is required to get?
Careful. This is inverse wavelength, right? So as you get closer to 0, your wavelengths are getting bigger and bigger and bigger. As you get further away from 0, your wavelengths are getting smaller and smaller and smaller. For me, it's a little bit easier. Rather than thinking about it in terms of wavelength, I think about it in terms of energy. This would be photon energy. Photon energy would get bigger as inverse wavelength gets bigger. So that would be bigger photon energy. Bigger wavelengths are smaller energy. Okay, you bet. Let's take, okay, you got a different slope. We'll take a look. I'll take a look at that in a little bit. Let's hop to, let me make a note of those other questions in queue. Mastery question, set 2, problem 3. So the last unique problem I have is practice 3, problem 8. Oh, I have that highlighted right here. I've already got it open. Okay. So let's go ahead and take a look at practice problem set 3, number 8. This one, I think all of the instructors kind of agreed that the wording was a little bit weird. But not so weird that we thought the problem should be taken out. I'll read through it real quick. It's got a lot of words to it. We introduced the idea of Rydberg constant. We can model the energy of any state of hydrogen-like atom, ion A, where A has a nucleus with charge Z and 1 electron. The relationship is related to the Coulomb's law, looks similar, but is really based out of quantum mechanics. And we get this equation that is essentially the Bohr model energy equation. We get the energy of an atom is equal to negative Z squared, Rydberg constant, times 1 over n squared. It writes it a little bit differently. Again, I like to write mine in this kind of suggestive way, where we could do a y equals mx. We could do another plot if we wanted to, even though it doesn't ask us to do that. It says, what is the energy of the system in the ground state relative to the n infinity? What's interesting about this is those n values. Now, there's a lot of kind of conceptual understanding that's necessary to make sense of this. These n values are counting numbers. They're 1, 2, 3, 4, 5, and they're representing stable orbits or just kind of solutions to the equations of interaction between the nucleus and the electrons. And we've got our first solution, or we've got a second solution, or our third solution, so on and so forth, up to infinity. But since it's inverse, we can kind of think about this in terms of an energy well. We've got our like n equals 1 there, n equals 2, and then we get up, and as we go up, the 1 over n gets closer and closer together, and they all kind of start stacking up together. Right? This is because if you had 1 over a billion squared versus 1 over a billion and 1 squared, they're about the same. And we essentially define this top value as energy of the atom equals 0. All of the other states are below that energy of the atom. So in that case, we just want to consider the lowest possible state, the n equals 1. So we're just going to say energy of the atom is equal to z squared, negative z squared times the Rydberg constant, 2.18 times 10 to the minus 18. Double checking on my equations sheet. Always keep an equations sheet handy. I want to make sure I don't get that wrong. Negative 18, okay. Times 1 over n squared. If we are looking at the ground state, which is part A, that's just going to be 1 over 1 squared. Now, each of you is going to have a different atom to consider. Mine is beryllium, Be. Again, equation sheet handy. I look at the periodic table. Beryllium has 4 protons. Z, if you remember from week 1, Z is number of protons. So I'm going to have, this is for part A. I'm going to have 16 times 2.18, and that's going to be my answer. For part 2, it's what's the energy required to ionize the system when it's in the n equals 4 state. Couple important ideas here. I'll draw on some other lines. N equals 3, n equals 4. In order to do this, we need to have the definition of what ionize means. So again, reading the definitions, ionize means we take this electron and we just completely send it out. So we're going to go from the n equals 4 all the way out. Now this means I'm going to have a difference between two energy levels. And so we're going to be looking at, instead of the energy of the atom, for part B, we're going to be looking at the change in energy of the atom. That's going to be negative z squared. Again, for me, since I've got beryllium, it's 4 squared, times the Rydberg constant, 2.18 times 10 to the minus 18, times, this is essentially becomes a Rydberg equation where I've got 1 over n final squared minus 1 over n initial squared. So I'm going to have 1 over infinity squared minus 1 over 4 squared. Now, if you don't like infinity squared, I don't blame you. If the idea of this going to infinity bothers you, plug in 100 million. 1 over 100 million squared, approximately 0. This thing is approximately 0. So that means our change in energy in the atom, the amount of energy we need to put in to ionize is going to be negative 4 squared times 2.18 times 10 to the minus 18 times negative 1 over 4 squared. I got a lucky number. I happen to get the situation where, you know, it's my negative 4 squared and my 1 over negative 4 squared cancels, and I just get 2.18 times 10 to the minus 18 joules for my answer. The Rydberg calculations do take a lot of conceptual understanding to get at, but once we have that conceptual understanding, it's really just math. So hopefully that was...
Part of the problem, you got 1 over infinity as your answer? Or sorry, you got... What did you get for the first one?
For this one?
Mm-hmm.
For part A, I didn't finish calculating. I'm going to have negative. I'm going to have negative 16 times 2.18. Ground state is n equals 1. So I just had 1 over 1 squared.
Thank you.
So that was practice set 3, problem 8. Ooh.
On the ground state, or that part A, why wouldn't it be 1 over like n final squared minus 1 over n initial squared?
So there's a difference in asking for the energy of a single state versus asking for the energy of changing states. Right, so if you look at question 8, what it's got there, this equation is the energy for a single state. This delta E is essentially just taking 2 of these and subtracting them from each other.
Gotcha.
So so it's like the first state, or the final state minus the initial state versus just one level.
Okay.
Okay. So I see some new questions getting tossed on there. Practice problem set 3, 5 and 7. Mastery question set 3, problem 4, part B. Okay. Since we're in practice set 3, I'll go ahead and do 5 and 7, and then we'll move on to the mastery questions. I haven't looked at these yet, so hopefully I know how to do them. Let's take a look. Problem 5. Emission of a 1,282 nanometer photon lowers an electron in hydrogen from n equals 5 to which quantum number n? Calculate it rather than looking it up. Whew, okay. Interesting wording, but has some key terms that clue us into what we're doing. So, emission of a photon means that we should be dropping in energy. The electron should be going lower in energy, so the n equals 5 should go down to 4, 3, 2, or 1 of those. And it lets us know that there's a change in quantum numbers. So all of those things should hint to us that we're looking at a Rydberg type equation. So we're actually going to be looking something similar to part B. Let's go ahead and calculate. Now these calculating n values are some of the trickier problems because sign errors, flipping your signs, can cause really big mathematical problems. So this is practice 3, problem 5, and I think problem 7 is pretty similar. Oh, problem 7 is a little bit easier than this, but that's okay. We'll start with the more challenging one since we just did a problem similar to this. So I'm going to have 2 options for my Rydberg equation. This is emission, so I'm going to use the easier equation for this case. There's one that really focuses in on the change in energy of the atom versus the energy of the photon. I did a problem about that yesterday, and we'll do it a little bit later. That's going to be mastery question set 2, problem 2 gets to that. But this one, since it's specifically emission, I can go ahead and use the Rydberg equation that's designed for emission. 1 over lambda is equal to the other Rydberg constant times 1 over n1 squared minus 1 over n2 squared. This equation is only for emission. And this is the part I always have to make sure I do correctly. N1 has to be smaller than N2. So that way I've got, N1 has to be smaller than N2. So in this case, since I know it's emission, at this point we just plug things in. We don't need a lot of conceptual understanding after we realize that this is what it's asking us to do. We can just start plugging in our different things. I've got 1 over 1282 nanometers. I'll go ahead and put my conversion factor down there as well, which is 1 meter has 1 times 10 to the 9 nanometers. Lots of nanometers in a meter. It's equal to, again, equations sheet. Make sure you get the right version of Rydberg's constant because there are 2 different ways to think about it. This is a different constant. 1.097 times 10 to the 7 inverse meters times 1 over n1 squared minus 1 over 5 squared. And at that point, you just solve for n. You just solve for n1. Hopefully not making any sign mistakes. I think since we use this version, we're less likely to make sign mistakes because it is emission. We can do that. Let's go ahead and we know we should get a whole number. So let's go ahead and start plugging things into calculator and see what kind of answers we get. Be very careful with your positives and negatives. They can really mess things up. Okay. Let's see. I'm making sure I didn't mess this up. Okay. I think we're okay. I already think I know what the answer should be, but we'll see. Okay, so I've got 1 divided by 122.82 times 10 to the minus 9. I'm going to divide that over, divide by 1.097 times 10 to the 7. Gives me 0.0711 is equal to 1 over n1 squared minus 1 over 25. I'm going to bring the negative, so I'm going to, let's actually plug in what one, let's just add that plus 1 divided by 25. It gives us 0.1111 is equal to 1 over n squared. So we'll inverse and take the square root. Inverse square root. And 1 is equal to 3. I actually get, the math was done really well. It was 3.0000. So sometimes you get things that are like 3.09, 3.1 something, and you just have to recognize that there's some rounding errors. But that's how we do that one, recognizing that we can use this version of the equation. The connection between that style of the equation and the other style of the equation has to do with how we relate the energy of an atom. This is going to be practice problem set 3, problem 7. One of my favorite units for energy is electron volts. Now this is a relatively useless unit of energy for everyone besides chemists and atomic physicists. It's the energy scale of electrons. So this is going to be problem 7. And again, equations sheet has your conversion factor for electron volts to joules, or vice versa. Here's the reason I like electron volts. I often have a hard time remembering 2.18 times 10 to the minus 18 joules. I find it much easier to remember 13.6 electron volts. That's kind of the main reason we do unit conversions. The human brain does a really good job dealing with numbers between 1 and 1,000. You get numbers a lot smaller than 1 or a lot bigger than 1,000, and our brains kind of don't process them as well. So electron volts is kind of the energy scale of visible light. It's on that order of photons in the visible spectrum. So it's kind of handy for that. We can go ahead and take our, now I might have different numbers than you, but I've got 3.66 electron volts. I'm going to use my conversion factors, get electron volts to joules. It's somewhere on here. There it is. I've got 1.602 times 10 to the minus 19 joules per an electron volt. that will give me 3.66 times 0.602 5.863 times 10 to the minus 19 joules. I don't know if that's in the visible spectrum yet. So that's going to be part one of the question, or the first box in the question is what's the energy in joules. Then I can take that and I can use this relationship. The energy of the photon is Planck's constant times the speed of light divided by wavelength. And I can say wavelength is equal to 6.626 times 10 to the minus 34 times 2.99 times 10 to the 8th divided by 5.863 times 10 to the minus 19. And that should give us wavelength. Inverse times 2.99 times 10 to the 8th times 6.626 times 10 minus 34. And I get 3.378 times 10 to the minus 7 meters. Conversion in my head, 337 nanometers. A little squashed there. So after doing that, this is actually not going to be, my case was not in the visible spectrum. It's going to be just outside the visible spectrum. We typically think of the visible spectrum as 400 to 700 nanometers. So anything bigger than 700 or smaller than 400 is going to be outside the visible spectrum. In this case, with 337 nanometers, we're looking at something that's actually going to be in the ultraviolet section of the electromagnetic spectrum. So that was all the practice problems.
Yeah, that makes sense.
Yeah, so it really comes to unit analysis and having that conversion factor, and then relating it to the properties of light.
I didn't make the connection between EV and J.
Yeah, and that's one where, you know, it's a problem when we have classes in person as well. I mention it very quickly, and we don't necessarily do a lot of practice problems on it, and if someone was distracted for a little bit in class, sometimes they miss it. Same thing with the videos. I know it's mentioned in one of the videos, but I can't tell you where or how carefully they mention it. It's just kind of like, oh yeah, you can do that conversion, right? Week 2, we assume you're good with conversions, but making that connection is important, and especially this problem doesn't define EV anywhere, so that would mess it up. The rest of the questions I have in the queue are all from mastery. Oh wait, no, I lied. I was going to say all from mastery question set 3, but they're mastery question set 2 and set 3. I wrote down the wrong problem there. Mastery question 3, 4B. Okay. Let me go ahead and open that problem. I'm just going to take a look at what these are real quick, see if they relate to each other. Okay. Wait, hold on here. Okay, it's hydrogen atoms. Okay, so 4B I'll do real quick because it's kind of relating to the other problems we're doing. So this is going to be mastery question set 3, problem 4B. And it's going to actually relate to the previous problem we were doing. And then I'll get on to those other mastery questions. So this one is, again, mathematically not entirely complicated, but conceptually to get to the math is a little bit tricky. So let's go through the words for it. So this is mastery question 3, problem 4B. So the energy needed to remove the outermost electron completely from an atom is called its first ionization energy. In terms of the Bohr model, ionization energy can be considered a process in which the electron moves from the lowest energy level, ground state, to an orbit of infinite radius. So that was really giving us our n values secretly. That was n equals 1 to n equals infinity. If you don't like n equals infinity, just put n equals 5 trillion. Almost infinity. Calculate the ionization energy for 1 mole of hydrogen atoms. Whew. So again, this problem, you'll notice a lot of these problems, the mathematics is all going to be addition, subtraction, multiplication, division, but getting the conceptual connections between the words and the math it's trying to get us to do. Recognizing that n equals 1 is the ground state to n equals infinity. This is actually really similar to, I'm trying to remember which question it was. I think this is similar to practice set 3, problem 8. One that we just did. But we're essentially going to end up with delta E equals negative z squared times I don't know why I put a parenthesis there. Rydberg constant times 1 over n final squared minus 1 over n initial squared. Notice this is not the same Rydberg equation we used just moments ago. This version of the Rydberg equation is really talking about how the atom changes in energy, looking at the difference between the orbital energies, depending on the final and the initial. Our change in energy of atom could be positive or it could be negative. But when we look at the wavelength of light either being emitted or absorbed, that always has to be a positive wavelength of light. So there's a little bit of conceptual difference there that's really important in terms of our mathematics if we wanted to relate this to wavelength and the idea of whether it's being absorbed or emitted. But in terms of this problem, we'll be able to just calculate the change in energy of the atom for hydrogen. So it's hydrogen, which means Z equals 1. And we can start plugging things in. We're going to have our change in energy for the atom is going to be equal to negative 1 squared times 2.18 times 10 to the minus 18 joules times our final is going to be 1 over infinity squared minus 1 over 1 squared. This is going to go to approximately 0. And we're going to get the change in energy of the atom in order to ionize it is going to be, notice the negative 1 squared, those will multiply out. And we'll just get 2.18 times 10 to the minus 18 joules. This is, again, important conceptual idea here. This is per an atom. And what the problem is asking for is kilojoules of energy per mole. So after we kind of recognize the Rydberg equation we're looking at in terms of the atom change, and we recognize the ground state to the highest possible excited state, infinity, again, like 5 gazillion. Now we're just doing unit conversion. So I want to get it in terms of kilojoules per mole. So I will do 1 kilojoule has 1,000 joules. And I will do 6.022 times 10 to the 23rd things per 1 mole. In this case, the things is going to be atoms. And I just go ahead and do that multiplication through. 2.18 times 10 to the minus 18 times 6.022 times 10 to the 23rd. Divided by 1,000. And I get 3,1, oops, no, I just flipped those in my head. I get 131, 2.8 kilojoules per mole. Whew, okay. So let me see. I want to make sure I'm not neglecting people from earlier. Emmy, did you go check out the video for Mastery Question 2, number 2, or do you still want to see that? So, Mastery Question Set 2, Problem 2. This is a Rydberg equation problem. It gives very little information in the problem. So I'll read it real quick because it's a really short question. Calculate the wavelength in micrometers of a photon that is produced when an electron drops from n equals 5 to n equals 4. So in terms of starting information we get very little information, right? All we get is this kind of like, oh, n equals 5 to n equals 4. We need to recognize the concepts and the terms within the problem that tell us what we're doing. So calculate the wavelength of a photon when an electron drops. So that means that we're going to be using something like the Rydberg equation. So I'm going to use, since it's emission, it's a drop, I can go ahead and just use the 1 over lambda case. This one's a little bit easier mathematically, but I think it hides the important concepts a little bit. So I like the other equation more. You can go watch Tuesday's office hours for that. This is going to be Rydberg constant times 1 over 4 squared minus 1 over 5 squared. Solve for lambda. In this case, the Rydberg constant, this is for the inverse wavelength version. That's going to be 1. I got to check. I'm going to get it wrong. 1.097 times 10 to the 7. 097 times 10 to the 7 inverse meters times 1/16 minus 1/25. Remember, if we're using this version of the equation, we have to have it such that this parenthesis is a positive number. So we always have to have a, sorry, I'm trying to make it so my whiteboard's wobbling a little less. We always have to have n1 be the smaller number, n2 be the larger number. Let's go ahead and do 1 divided by 16 minus 1 divided by 25. This is going to give us 0.0225 when we calculate that. Multiply. Oh, you'll notice I left off my z squared. Something interesting, I feel like this might be a typo in the problem, but it doesn't give a z value. So I'm going to assume that it's a z equals 1. Most of the problems we do when we're looking at this are hydrogen, so z equals 1, unless specifically stated otherwise. So that's why I left off the z equals 1, because 1 squared is just 1. And then I'm going to do times 1.097 times 10 to the positive 7. And I get 1 over lambda is equal to 2.468 times 10 to the positive 5 inverse meters. You'll notice that this is inverse wavelength, so I'm going to go ahead and take the reciprocal so I can get lambda is equal to 1 over 2.468 times 10 to the 5th meters. Inverse, and I get lambda equals 4.051 times 10 to the minus 6 meters. The question asks specifically for the answer in micrometers. Always check your units. We can do a quick conversion to micrometers by doing let's see, I want 1 times 10 to the positive 6 micrometers. There's a lot of micrometers for every meter. Meters cancels out. The 10 to the minus 6 times 10 to the positive 6 cancels out, essentially, and I get 4.05 micrometers. Again, this is for my numbers 4 to 5. Conceptually, you should be able to do the same thing for yours. 5a. The emission lines of one electron atoms and ions can be fit with the equation describing the spectrum of hydrogen. Same Rydberg equation we have. Energy should be delta E in my opinion, but that's okay. The energy of the change is equal to Rydberg constant times z squared times 1 over n final squared minus 1 over n initial squared. Calculate the energy in joules for the photon associated with the transition of the electron in helium for n equals 2 to n equals 1. So this is energy of the photon. So we want the energy of the photon for helium going. So we don't need this wavelength equation. We're going to switch to the photon equation. So let's go ahead and analyze the problem. It gives us some hints. It gives us some ideas. This is Mastery Question Set 3, Problem 5. I read 5A. Did you ask 5A? You did ask 5A. Good. I thought for a second I did the wrong thing. Problem 5A, given things, n equals 2, n equals 1. We're given the equation. We're given that it's helium in the plus state. Always identify what the question is asking for. Photon energy. So, inferred information. Helium corresponds to the Z equals 2. Need the periodic table to get that bit. We're going to go ahead and say the energy of the atom, and I'm going to do this in terms of the change in energy of the atom, the way I like to do it, is equal to negative quantity 2 squared times 2.18 times 10 to the minus 18 times, and it says the transition of the electron from n equals 2 to n equals 1. Now, there's a couple different things. N equals 2 to n equals 1 is going to be from, so we're going to go from 2 to 1, so n equals 2 to n equals 1. So that's going to be an emission. That means my initial state is n2, my final state is n1. So I'm going to have a 1 over 1 squared minus 1 over 2 squared. The reason I did that thinking right there is because I wanted to make sure that if I got an energy, you can notice whether you do absorption or emission, the way that the energy of the atom is changing is different, but the wavelength is going to be the same. So the energy of the photon is going to be the same because that gap is the same. The delta E is the same. But it switches the sign from positive to negative, whether you're gaining energy or losing energy. And that's going to be important because we would have to do a sign flip. You'll see in just a moment as well. So at this point, run your calculator. You're going to have 1 minus a quarter times 4. So 1 minus 1 divided by 4. This is 0.75. That's that part. And delta E of atom. Oh, it is going to be important. Okay. Is equal to, so I'm going to have 0.75 times 4 times 2.18 times 10 to the minus 18. And I'm going to get negative 6.54 times 10 to the minus 18 joules. The atom is losing energy, right? It's dropping in energy. So I end up with the atom losing energy. The photon energy, since whether it's gaining or losing energy, the energy of the photon is still the same, I'm going to say the energy of the photon is just going to be equal to the absolute value of the energy of the atom. So that means the energy of the photon is 6.54 times 10 to the negative 18 joules. We have to be careful. This is totally fine when we're just calculating the energy of the atom, energy of the photon. We have to be careful when we're calculating our n values. That problem we did earlier, this sign flip from the absolute value can totally mess up your order of n final, n initial. So you have to be careful with your logic when you're working on that stuff. But that should be how we do a lot of these Rydberg equation type problems. Did that make sense, Nick?
Yeah, that's it.
Great. Okay. So we're going to take a look at mastery question set 3, problems 8 and problems 10. And I think I just took a look at problem 10. I think problem 10 is going to be removed. It might be easier just to make it worth 0 points. I don't know what we're going to do for that. But that one is actually material that we're kind of getting to at the end of this week, but as instructors we agreed we wouldn't be testing you on it until next week. So it won't be on the quiz at the end of the week. But let's go ahead. This is getting into quantum numbers, which is, I made the video about it because this gets to some of my favorite stuff. So, quantum numbers are essentially an addressing method for different answers to equations, right? So this is mastery question set 3, problem 8. We've got a nucleus. We've got some electron. That electron and the nucleus interact with each other through the Coulomb force. Positive charge attracts negative charge. The electron is also moving around in some physical space with some kinetic energy. When we start solving this kind of like constrained interaction type idea, instead of getting one answer, we get a set of answers. We get things that look like sine of theta. We get things that look like cosine of theta. We get things that look like e to the x. We get things that look like e to the ix. We get a whole bunch of different functions. We don't need to know those functions. What we do instead of knowing all those functions, and if you watch Dr. Scott's video on quantum numbers, you'll see a list of what these functions actually look like. They're big mathematical equations. So instead, we use essentially an addressing system in terms of 4 different numbers to tell us which function we should look at, which mathematical function we should look at. This is the principal quantum number. This is the angular quantum number. This is the magnetic quantum number. Sure. And this is the electron spin spelling. Let me just do a quick yes/no check in chat so you can click on participants and click yes or no to this question. You watched the video on quantum numbers already. Mostly yeses. Okay, cool. I just wanted to know how much detail I had to go into here. So this is going to be from 1 up to infinity by steps of 1. This is actually the same n value we were just using for the Rydberg equation. This is going to be from 0 up to n minus 1. So there's going to be some relationship between these two which restrict what values of L are allowed. This is going to be from minus L all the way up through 0, all the way up to plus L. So there's going to be a relationship between these two which causes some restriction. And this is going to be plus a half or minus a half, and that's it. So when we have question 8, it says, how many different magnetic quantum numbers are possible for an angular momentum quantum number of value 3? For me, I've got 3. You might have a different number. Select a letter corresponding to the correct number of possible magnetic quantum numbers. So if L equals 3, then my m sub L, so that's my angular quantum number equals 3, then my m sub L could be minus 3, minus 2, minus 1, 0, 1, 2, or 3. All the way from negative L up to positive L by steps of 1. And then I just count how many there are. 1, 2, 3, 4, 5, 6, 7. So I have 7 possible. That means when L equals 3, I'm going to have 7 different orbitals which we typically draw as 7 different boxes. 1, 2, 3, 4, 5. Good, I got it. Okay. So this would be 7 orbitals. Trying to not get too far into next week's material yet. Each box, each orbital can have an electron with a spin up or an electron with a spin down. That's the plus a half or a minus a half. So each orbital can hold a spin up or a spin down. And we see (14) possible electrons fit in 7 possible orbitals. That's way beyond what the question asked. The answer was 7, but I really like this stuff, so I'm going to get carried away. The last thing I'll mention before we move on, because I think this is neat, if you look at the periodic table, you'll notice that the F block, which is the L equals 3 block, is 14 long because it can fit 14 electrons. So all of this relates back to the periodic table. All of our quantum number stuff, all of our energy understanding is going to relate back to the periodic table and the way that these things react, the way that these things have physical properties, the way that they interact with each other. It's all going to relate back to this quantum mechanical idea. Question 10, like I said, I think will get changed or switched to 0 points or something like that because we agreed to move that off of this week to next week. So I'm not going to answer that one this week because I don't want to confuse people too much.
You mind on 7C?
Let's see. You said 7C? 7C. Which of the following orbitals are not allowed according to the quantum number guidelines in the text? And I see an answer right away. Again, I don't know how this is randomized or not. But we're going to need one more piece of information here to do it. So I'm going to switch to problem 7C. And in order to do this, I'm gonna draw out some extra ones here. Oh no, I'll leave it as this. So there's an important mapping of quantum numbers. Chemists a while ago agreed that having everything just in terms of numbers kind of made it too easy to confuse what was going on. And it was also kind of experimentally determined earlier. So we have this mapping of L equals 0, we call S. L equals 1, we call P. L equals 2, we call D. L equals 3, we call F. And next week we'll talk more. We talk about it a little bit this week, but we'll talk about the periodic table and the S block, the P block, the D block, and the F block. That was part of what I just mentioned. The reason that's important is because question 7C gives us a list of possibilities. At least I get this list of possibilities. You might have a different list of possibilities. 3D, 1P, 8S. And it says, which of these is not possible based off of the guidelines? We have to know how to read these subshell, these subshell designations in order to translate them to quantum numbers and figure out what they mean. So 6F means n equals 6, L equals 3. 3D means n equals 3, L equals 2. 1P means n equals 1, L equals 1. And 8S means n equals 8, L equals 0. If we look at our rules, L, since we're only looking at n and L's, n can be anything, so n is not going to restrict us at all. L has to be less than n minus 1. So I look at L n minus 1, L can be 5, 4, 3, 2, 1, 0. We're good. Here, n equals 3, L can be 2, 1, or 0. We're good. Here, n equals 1, L has to be 0. So in this case, that one's not going to be good because n minus 1 would be 0. This L value is too large. N minus 1 would be 7. I could have 7, 6, 5, 4, 3, 2, 1, 0. I'm fine.
So when you're calculating L, you just divide n by the corresponding number with whatever letter it is.
Well, so what I did, essentially what I did was, let's look at this first one. And we'll look at it kind of in the thinking way rather than just the checking way. If n equals 6, L can be equal to 0 all the way up to n minus 1. So L could be 0, 1, 2, 3, 4, or 5. I've got a bunch of different options. I actually get 6 different options for my possible L value. So it turns out that in this case, I am within inside that because we recognize that we're going to have L equals 3. So it's one of my possibilities. And then for each of these, and I was kind of doing this in my head, if n equals 3, L could be 0, 1, or 2. Right? It's got multiple possibilities.
How did you get 3 for when n equals 6?
How did I get this L equals 3?
Yeah.
So I did that because of the F value, right? So I looked at this F value.
Oh,
So-
okay.
And I related it. I said, oh, if I have the F, that means L is 3.
Okay.
So all these L values, the letters after the numbers translate to different L values. We refer to this 6F, 3D, 8S. I'm not going to do the wrong one. We refer to those as subshell designations. They represent multiple orbitals, but they represent a shell or a subshell. Not a full shell, a subshell.